In AP Chemistry, a lot of the reactions we've been looking at through thermodynamics and prior have been in one direction. We take something and change it into something else, and typically that is favorable for the situation. We talked a little bit about enthalpy and entropy as driving factors, where enthalpy is all about the heat that is released or absorbed from a process changing. We kind of ignore work as a factor. And entropy is how energy is dispersed through a system as we have more and more configurations or less and less configurations. So typically we like looking at reactions that happen spontaneously or favorably, basically automatically, because they have a driving factor or two, either enthalpy or entropy or both, that are pushing the reaction along, like something releasing heat is a driving factor, or something increasing the number of possibilities, the number of configurations for the particles involved. That would be another driving factor for entropy. But just because something is pushed in one direction doesn't mean it can't go back the other direction. So I have a couple things here to represent some processes that are typically something you see going in one direction. So for instance, I've got a cup of ice water here. All right, this is a pretty well insulated cup, so as long as I don't, heat it up too much externally, it should hold the ice in here for quite a bit. And that temperature that it's going to reach a thermal equilibrium at with its surroundings, with room temperature, is high enough to get it to melt into a liquid. So we have a directional process where our ice is changing into a liquid from a solid. We're going through the melting process, okay? And in these conditions, it's only going in one direction. Salt is a substance that pretty easily dissolves in water. So when we throw salt into water, we expect it to dissolve. Maybe it takes a little bit of mixing, maybe you got to heat the water up a little bit to get it moving, but it just kind of happens in that direction. Now, chemically, we're taking the NaCl and we are breaking it into its ions, right? We get ion dipole interactions, intermolecular forces between our water molecules and those Na plus and Cl minus ions that make it more favorable overall than keeping the NaCl together with the ionic bonds. Okay, here I've got a can of soda. We did a lab where we looked at how much acid is in a typical soda beverage or in a fruit juice, things like that. In this case, we're looking at citric acid, okay, which a lot of us kind of looked at for our beverages. So acids are things that release H pluses, release protons, or you could say hydronium ions, H3O plus form in water, and that's how we define how acidic a solution is. So the citric acid in here is kicking off H pluses, right, to make the solution that it's sitting in acidic. The way a battery works is a redox reaction, reduction oxidation. So we have a transfer of electrons, but instead of having that transfer of electrons directly from one chemical to another, we cause them to wait kind of on a connection from one end of the battery to another for electrons to flow through something like a wire. Okay, so we have to hook them up to a system that allows electrons to move from one chemical to another. We don't have just a thing where chemicals smash into each other and the electrons transfer right away. We have to move the electrons from one spot to another. Okay, but like I said, just because these happen one way doesn't mean they can't go back another way. Reversible processes can be put back the other way. Some things are so difficult to do so, it's essentially irreversible, but under some conditions, it's not really a hard thing to do at all. And sometimes reactions do it automatically as it is. In our ice water over here, if I can keep this nice and cool at around the freezing point, I have water molecules in the liquid phase. All right, I have water molecules in the solid phase, and instead of just doing it in one direction and having one change to the other, like our solid changing to liquid and melting, we actually have some freezing. Okay, as long as you're at that freezing point, you have water molecules moving in between. Although we can't see it at the surface, there's a lot going on down on the molecular level, on the atomic level. We have water molecules constantly bashing into each other, and some of them slow down enough to reform back into that crystalline ice structure. And some of them get bumped around to have enough energy to move back out as a water molecule in the liquid phase. So we're constantly exchanging water molecules at the surface of this. Okay? So it's not just one direction. It's happening both ways, and it's happening at the same time. Okay, so we have chemical equations that represent these four processes that we are talking about. So typically, this is how we see these processes happen. We have H2O as a solid that melts into H2O as a liquid, right? Same chemical formula, but different phase of matter. We have solid salt, NaCl, that dissolves and breaks up into its ions, into Na plus and Co minus. Those are both aqueous. They're floating around in the water. We have the deprotonation of an acid, right? An acid lets off an H plus, and an H plus is really no more than a proton. So if the acid is deprotonating, or it's going through deprotonation, it's just kicking out an H plus. It's just a fancier way of saying that. In both of these, we can just also say dissociation for breaking into ions, but you like our fancy terms. So our acid deprotonates, it dissociates, it breaks up into the H plus that makes the solution acidic. And we've also got this anion that's left over the rest of the acid, the conjugate base, if you will. And finally, for our battery, we have a whole bunch of stuff. We've got lead solid, lead oxide solid. We've got HSO4 minus. This is an acid, all right? But it's also a base. This is both an acid and a base. It can go either direction depending on how we push it. We've got H pluses, right? And this goes through a redox reaction to give us PbSO4 solid and water as a liquid. Okay. But it doesn't have to be this way. We can set this under conditions where we reverse the reaction the way we usually write it. Okay? Just because I put this on the left and this on the right doesn't mean it always has to be that way. It's just tradition. It's just what fits a certain set of conditions. If I, say, put this at the right temperature, I put it at 0 degrees Celsius, okay, or I turn it lower than that, I can have the opposite process happen. My water can freeze back from a liquid to a solid. Okay. I can also have Na plus and Co minus find each other and recrystallize together as an ionic compound. Right? This happens, very rarely with NaCl. It's a strong electrolyte. It breaks up totally in water. But if we saturate the solution and we pump it full of as much NaCl as we can, then it's a lot more likely. We're going to have this, again, boundary of NaCl and water that is going to keep trading between Na plus and Cl minus and having the original solid. Okay. We can precipitate a solid going this direction. Now, we don't usually precipitate NaCl outside of a saturated solution because it dissolves really well. Typically, we look at precipitation with something that is not so soluble. So let's change this a little bit just so it fits a little better to the situation. We're going to use silver chloride instead of sodium chloride. Goes through the same process, but it's way less soluble. So we don't have to load up a solution with as much before we hit that point where we are going both ways. We can have the dissolving and the precipitation at the same time, down on the nitty-gritty atomic level. Okay? The deprotonation of our acid here also reverses. We talked about weak acids and weak bases. Okay, those are weak electrolytes. They're defined by the fact that they partially stick around as their molecular form. They don't break up totally, in the sense that we have some of these go and break off an H plus and some of them don't. Or better yet, we're constantly going through the process of some of these breaking off into H pluses and some of these picking up an H plus and reverting back to the molecular acid. And again, we can call that protonation. We're picking up that H plus. We're protonating this anion over here. Okay, and finally, this monster going on down here. This is for a lead acid battery, like in a car battery. When you run your car, your alternator does some stuff. I'm no mechanic, but things turn, all right, and generate electricity to recharge your battery. Okay, so if your car ever dies and you go and get it jumped, you have someone else's battery hooked up to yours and you give it some juice, that's great and all, but you also want to run your car for a little bit so it can recharge that battery. When we supply energy in, we can turn this around. Our oxidation and our reduction flip, okay? They go the opposite direction. In all these cases, we have the same chemical equation, but it gets turned around the other way, okay? So I could easily write this flipped around, or this flipped around, or this flipped around, and it can talk about an equally viable process. It just depends on what's happening in your specific set of conditions. What have you set up the substances to do? What are they going to do? Okay. Now, I mentioned before that some of these are happening constantly. It's not like we either do it one way or the other and it only happens one at a time. When we keep water at the freezing point, it stays in that exchange. We continue to have this process go both in the melting and the freezing direction. All right? So our water is continually going between the solid and the liquid, or back from the liquid to the solid. Okay? So a reversible reaction is not like, oh, it can be turned around. It is always going in both directions. These are happening simultaneously. Okay? So we are simultaneously melting and freezing our water when we're holding at the freezing point. Okay? We're constantly making ice and liquid water back one way or the other. We got plenty of atoms, we got plenty of molecules to do this with. So there's no reason why we can't do them at the same time if we've got the right conditions. For our precipitate here, for our AgCl, AgCl does not like to dissolve in water very well. Even that ion dipole intermolecular force is not enough usually to break this ionic bond, but it can a little bit. But it's not like water goes through and says, oh, we'll dissolve, 4 of these, and then, oh, we did 4 of them, that we're good. We're just going to stop there. And then the process stops. Instead, we are constantly dissolving AgCl and breaking it up, dissociating it into its ions, okay? But the magnitude of how much Ag plus and Cl minus that we make compared to the AgCl that remains, it's not even close. We still have way more of this, all right? So this is a case where we are constantly dissolving and breaking this up, but we also precipitate back to the AgCl, okay? Both processes happen at the same time, but that also doesn't mean we have to have the same amount of this as this, okay? Same time, but this amount does not equal the amount of this stuff on the right side, which is a little bit tricky. Okay? For our acid here too, we have this happening constantly. I think I said before, our acid does not just sit around and like, oh, okay, I threw out a couple H pluses and now I'm good. I'm just going to wait. It's constantly picking those H pluses back up and then getting them out, picking them up. Okay? But just like with our AgCl up here, we have sort of leaning of our reaction. Just because they're both going at the same time, okay, does not mean that the amount of our acid over here equals the H plus and the anion left over. And finally, the redox, the big nasty one. Same thing, all right? If you're running under the right conditions, you can have, a battery that is constantly recharging and being used at the same time. You're constantly just kind of moving that reaction. Now, does that mean that you just don't have a reaction going? No. If your phone is still on and still plugged in, then obviously you're using some electricity there. Some energy has to be moved and transferred and changed into different forms. So if you're doing something like this, then it has to be going both ways at the same time. All right, we are both fueling the reaction to rebuild our reactants and also using them at the same time. All right, both reactions happen at the same time. That is a reversible reaction. Now, what makes it an equilibrium is when we can't tell that the reaction is happening. And I'm not just talking about like looking at it and being like, oh, I can see the change, or I can't see the change. Even down to the atomic level, when we measure concentrations, okay? For something like this AgCl, okay? When I precipitate out AgCl, if I go and measure in the concentration of Ag plus and Cl minus, maybe I get a conductivity tester, I'm not going to see like, this number that is constantly increasing and increasing as I continue to pump out Ag plus and Cl minus. And I'm also not going to see it continually falling more and more and more as we remake AgCl. To get to the equilibrium, we might have to break a bunch of these guys up or put them back together. But the point of equilibrium is when we no longer see that change. The rate at which we break up AgCl into its ions is the same as the rate going back the other way. Okay? This is why we needed kinetics in order to understand a lot of stuff that happens in chemistry. Equilibrium is just when you have the rate going one way equal to the rate going the other way. All right? So all of these are reversible reactions, but they're not at equilibrium until the process going this way is the same as the process going this way. In the case of our water, right, we would not see a change in how much ice is there compared to how much liquid water is there, because as long as we are taking some of our solid and changing it into a liquid, at the same rate we have liquid changing back into the solid. Okay? For our acid, we don't see the pH continually change back and forth and it's going up and down. We have a reversible reaction that at equilibrium means that as we break up into ions, they go back to becoming the molecular acid. So it's not like we constantly are like pumping out H pluses more and more and more, or putting them back together and getting them out of the solution. Okay? Those reactions are constantly happening, but because they're happening at the same time, at the same rate, it's like there's no change. You can kind of imagine it like a busy restaurant. You don't have the same customers all day. People go in, they order, they eat, and they leave. But you kind of have the same size of crowd as the day goes on. Maybe fluctuations here and there, but you have a family come in, a family leaves, two families come in, two families leave. You end up with the same rate of people going in as people coming out. That is equilibrium, just at the chemical level, where we're dealing with atoms and ions and stuff.